So let's move to the topic of Lagrange multipliers and extrema on curves, and these two are connected. So we've taken a look at the concept of local extrema. These were the peaks and craters of the function f, okay? And, an analog to asking that question is asking where are the peaks and craters of the Rocky Mountains, okay? We also talked about absolute extrema. That's the highest and lowest part of a function on a set. Question that is analogous to that is what is the highest point in Wyoming and what is the lowest point in terms of altitude in Wyoming? And it could occur at the peaks and craters of Wyoming, or it could occur at the boundary. Say there's a mountain between Wyoming and Montana, and the highest point could occur at the boundary there. So the analog question to absolute extrema is what is the highest point in Wyoming, for example. Let's move on to the question of finding extrema on a curve. And the analog to that is what is the highest point in a certain hiking path along the Rocky Mountains, for example. Okay, so this is the question. So we're not asking for the absolute highest point in Wyoming, say, and we're not asking for the peaks of mountains along a mountain range. What we're asking is for the highest point along a path, a hiking path that we define, and then look at the altitude along that path. So how do we solve that problem? So the mental image to have here is this graph that you see here. The graph is orange, but we're not interested in the peaks of that graph, nor are we interested in the highest point of that graph in a given set. What we are interested in is the highest and lowest points along just this hiking path. Okay, so where are the highest and lowest points along just that red path? Okay, notice we have a curve C in the xy plane, that's in the domain, and the function maps that curve up to the red curve you see on the graph. And so we're looking for the extrema just along that graph. So this theorem here will aid us in finding the local extrema along a curve, and even the absolute extrema along the curve. So let f be a differentiable function in a region of R2 that contains the smooth curve C. This smooth curve is given as a level curve of a function of two variables. So the curve is just given as gxy equal to 0. Also, assume f has a local extreme value on C at this point AB. What consequences do we get? We get that the gradient of f is orthogonal to the line tangent to C at P. Okay? So it's orthogonal to the curve at the point P. And furthermore, assuming that the gradient of G, this function we have there that gives us the curve, assuming the gradient is not 0, then it follows that the gradient of f and the gradient of g are parallel. And what does it mean for two vectors to be parallel? It means that you have some kind of some scalar constant you could multiply of one to get the other. Okay, so we have this relation. That scalar constant is called the Lagrange multiplier. Okay, and despite this section being called Lagrange multipliers, okay, our objective is not actually to find the Lagrange multiplier. It's to find the points at which extrema along a curve occur. So why does this work? Well, there's two things to consider here, okay? The first is the curve. And how can we describe the curve? I mean, one way to describe a curve is to give a parameterization, right? Some r of t. That would, that maps to the plane. That would give you a curve. Another way is to give it as a level curve, and that's what we're choosing to do here, okay? So we take a function of two variables, and we set it equal to 0, and that will then give us the curve, and we call this the constraint, okay? And you'll have to recall that when you take a function of two variables and set it equal to a constant, you do, in general, obtain a curve. But we may also describe a curve by r of t, and here, just for the purpose of understanding, let's suppose that the curve that's given as a level curve is also described by a parameterization, okay? Then we have this here, okay? And this is because once you plug in the curve into G, you're going to get 0. That's how we get the level curve, right? The level curve is the curve that the function equals 0. So we're just plugging that curve into G, and of course we'll get 0. Now, taking the derivative of both sides, the derivative of 0 is just 0. But what's the derivative of this guy? Well, the derivative of this is going to be obtained by the chain rule. So we use the chain rule, and we could then write this expression as this. And here's what we need to focus on here, okay? What is this telling us? This is telling us that the gradient of G is orthogonal to the tangent vector of our curve, okay? So this means that the gradient of G is always orthogonal to the level curve. So everywhere along the level curve of G, the gradient of G will be orthogonal. That's one fact that we need to remember. So let's now take a look at the second component of why this works, which is the function, okay? We call the function the objective function, and it's the function of two variables which we wish to find the extrema on the curve C for, okay? So what we could do now is plug the parameterization, okay? Take the parameterization of this constraint, r of t, plug it in. So now we have a function of one variable. Once we plug in the parameterization, it's going to be just a function of t. And we take the derivative with respect to t, and this is what we get, same as above, only we don't have that this is equal to 0 everywhere, right? Instead, we do know that for functions of one variable, at extrema, their derivative will be equal to 0, okay? So at extrema of the function at the boundary, at extrema of the function at the boundary, we expect the derivative to be 0, and that means that at those extrema, the gradient in this tangent vector will be orthogonal, so we could say that the gradient of f is orthogonal to the curve at the extrema of the boundary function. So the gradient of G is always orthogonal to the level curve. The gradient of f is orthogonal to the curve at the extrema of f along that curve, where we're interested. So what does that mean? That means we should look at where the gradient of f is parallel to the gradient of G. Since at the extrema, both will be orthogonal to the curve, and if they're both orthogonal to the curve, they're both parallel. So let's conclude with this line of logic. On this curve, okay, given as a level curve, so we've described it two ways. Here it's just given as a level curve, and that's what we'll be using. At extrema of the boundary function, the gradient of f is orthogonal to the curve, and the gradient G is always orthogonal to the curve, because the curve is given as a level curve of G. And so that means that the gradient of f and the gradient of G are both orthogonal to C at the extrema of the boundary function. And so that means if they're both orthogonal, they're both parallel at the extrema of the boundary function, which means you could write the gradient of f as some scalar multiple of the gradient of g, since they're parallel. And this is a vector, right? So vectors are equal when each of its components are equal. And so you get two equations out of that. Fx equals lambda gx and Fy equals lambda gy. That's just breaking this up into its components. Circled here are the three important equations that will lead us to candidates of extrema, and so we must consider them. So here's also a summary of how we'll do this. So the method of Lagrange multipliers, in a nutshell, requires you solving these three equations to get candidates for your extrema. Once you get those candidates, you plug them into the function, actually look at where the absolute maxima are and the absolute minima. So these three equations give candidates for local extrema on the curve C. And for absolute extrema on C, we must also consider the topology of C and its boundary. The topology is just to say we should look at whether the curve is closed or open. Hopefully it's a closed curve in the sense it includes its boundary points, then we know a absolute extrema exist. And we must also consider the boundary. Okay, so you have to look at the endpoints for your curve. Okay. And the mental image that you could take here is by looking at this graph. So what you're seeing, the green circles there are the level curves of f. Okay. And that black curve there is the constraint curve. G, x, y equals 0. Okay. That black curve is the constraint curve. And notice the blue vector is the gradient of g. And along that curve, the gradient of g is always orthogonal to the curve. We expect that. That's what we derived above. Okay? But notice the gradient of f is not always orthogonal to the black curve. The gradient of f is always orthogonal to its level curves, to the green curves that you see, but definitely not the black curves. So once we reach the point P where the function has an extrema there, okay, then the gradient of f and the gradient of g are parallel. The gradient of g is orthogonal because it's always orthogonal. The gradient of f is orthogonal to the constraint curve. When you reach an extrema, the gradient of f is also orthogonal at that point. So let's take a look at an example. So we have our function here. That's going to be our objective function. And we want to find the absolute maximum and absolute minimum values of this objective function along the constraint given as the level curve of this function of two variables. Okay, so you're setting that equal to 0. We're going to get an ellipse there. Okay. And so we're going to have to solve the three equations that we've seen above. And so taking these partial derivatives, we get these two equations, okay, coming from 1 and 2 above there. And 3 is just the constraint curve, okay? And so what are we have these three equations. What are we solving for? We're solving for all points x, y that satisfy these three equations. Now it's three equations and three unknowns. Lambda is also an unknown, the Lagrange multiplier. But frankly, we don't really care to solve for lambda. Our end result is the points, not lambda. Lambda is a means to an end, not an end in and of itself. Okay. Something else to notice, that these three equations are nonlinear. And with nonlinear equations, it takes a bit of finesse to solve them. There's no formal theory, very well formulated in simple theory like there is for linear equations. But there are some guidelines for solving these three equations. Since lambda, the Lagrange multiplier, is a means and not an end, what we could do is try to eliminate lambda early on. Okay? We could do it in this example by noting that 2x plus y cannot be equal to 0 and satisfy all three of these equations. So you could see that because if it were 0, then x would equal 0, which means y would have to equal 0. But that would not work with equation 3. We could apply a similar argument for 2y plus x. And all that allows us to do is solve for lambda, so we could divide, we'll get that lambda equals this from the first equation, lambda equals that from the second equation. So you got to be, if you just jumped and divided by 2x, there would be no problem for this specific example, but you can get some kind of absurdities or miss some solutions if you end up dividing by 0. So you have to be a little careful. But once we do get lambda, we could then just set these equations equal to each other, and we get this right here. And cross multiplying and then simplifying, we end up with that expression there, this equation. We could factor x squared minus y squared into x plus y and x minus y. And so we get two solutions from eliminating lambda from 1 and 2, from equations 1 and 2. That's the x equals y solution and x equals minus y solution. Okay? And what we then do is take the solutions we got from 1 and 2 and plug them into 3. Okay, so first I'm going to start with the x equals y solution. Plug it into 3. 3 is right up here. And so you have x squared plus x times y, but we're plugging y equals x solution. So then y is also equal to x. So that's coming from plugging in y equals x. This was a y squared over here, but we're plugging in y equals x. So we get that there. And we solve and we get that x is equal to plus or minus 2 over root 3. And we use the x equals y solution. So if x was equal to plus 2 over root 3, then y better also be equal to that. And if x is negative 2 over root 3, then y better be equal to that. And that's where you get these two points. Notice that the x and y are equal in those. Okay. Next, we're going to plug the y equals negative x solution into 3. Okay, and now there was a y here. We just plug negative x. There was a y here. We plug negative x. And we simplify and solve, and we get x is equal to plus or minus 2. Now, y is equal to negative x, so whatever sign your x is, y is going to flip it with that minus. So, you have plus or minus 2 for x, you're going to get minus plus 2. And so we get 2 more points for candidates. That's going to be 2 minus 2 and minus 2, 2. Notice here that the y values are the negative of the x values there. And again, because we're looking at the y equals minus x solution. Plugging all our candidates, so what else should we look at? We should look at also, say, the boundary of the curve, but it's an ellipse. An ellipse closes on itself and hence has no boundary. And why do we even want to look at the boundary? Because we're asked to find the absolute maximum and minimum. Okay? So what we found there are the candidates for local extrema. Okay? And so we plug in these candidates for the local extrema into our function. We get 14 over 3. And for these two critical points, and so that's the absolute minimum. The absolute minimum is 14 over 3 and it occurs at these two different points. And we also plug in 2 minus 2 into our function and we get 10 for each of those. And again, when I say plug in, means go right back to the original function. And so if we wanted to plug 2 minus 2, we'd plug in a 2 where we see a x, and we'd plug in a minus 2 where we see a y. And so that's where these values are coming from. And 10 is higher than 14 over 3, so we know then that that's the absolute maximum on C. So a recap. We started with our three equations. We looked at equation 1 and 2, and generally it's a good idea if you could eliminate lambda early to go ahead and eliminate it. And so that's what we did. We of course had to apply an argument that, we're not going to be dividing by 0 when we solve for lambda. But once we did that, we got two solutions. We plugged those two solutions into equation 3, which is the constraint, and we ended up with the extrema, the points at which the function has extrema or candidates for extrema along the curve. And we plugged in each of these points into the function, and we now compare all of the points. We see that 10 is the highest value along this column, and so we say that the function has an absolute maximum of 10 on C, and they occur at these points. Okay. And here is the function that we just considered. You could see the red on the right hand side there. That red curve is the constraint curve. Okay. And the green lines that you see there are the level curves. And you could see that as you vary the point, you move along. And so right up here is going to be the absolute max, and right down here is going to be the absolute min, and likewise this had the same value, so they were both absolute maxes there, that point and the opposite point. Okay, and the local min were here and the opposite point there.